this first amount if I harvest at some time capital T, but then I can repeat the process and harvest at some time 2t and sometime 3t and sometime 4t. Now, if all these curves are the same, then it means that pt equals p2t equals p3t and so on. So that means this v infinity t can be written as, I can take pt out as a common factor, and then I've got e to the minus delta t plus e to the minus delta 2t plus e to the minus delta 3t and so on. So everybody's happy with that. And this can be written as a summation notation. Sigma I equals 0 to infinity, or in this case, sigma I equals 1 to infinity. Is everybody familiar with the summation notation? Anybody not comfortable with it? Okay? And then this would be e to the minus I times delta t. Okay? Now, the remarkable thing about this is that you can actually sum this up. Does anybody know what the sum is? Does anybody know what the sum of sigma I equals 1 to infinity x to the power I is? Do you remember? Anybody? X over 1 minus x. Who's like shocked to see that, or who thinks that looks familiar? Who thinks it looks familiar? You know how to check this result. You can just do this thing. You can say s is equal to 1 plus x squared plus x cubed plus x to the fourth. And you can say x times s is equal to x times 1 is x times x is x squared, and so on. So therefore, if you take this, s minus xs is equal to 1. So that means s is equal to 1, s into 1 minus x is equal to 1. So s is equal to 1 over 1 minus x. However, this sum goes from I equals 0 to infinity. But if you go from I equals 1 to infinity, then you get the extra x in, and that's why you get an x over here. So you can check that. Okay, so this can be written as pt, and you can also look at this up at the back of your book. You probably got the formula in. So this can be written as pt e to the I, e to the minus delta t, 1 minus e to the minus delta t. So you can write it that way. You can also then multiply top and bottom by e to the plus delta t. So then that's equal to pt into 1 into e to the delta t minus 1. So just multiplying top and bottom by e to the delta t, that cancels, e to the delta t, that cancels, and so then you get this term. So this is the expression for v infinity t. Okay, now what? Now we want to find the value of t that maximizes that expression. Okay, so now you've got to do a little bit of calculus again. So optimize. So one thing I didn't mention here is that if we want to maximize, we take the derivative. If we take the derivative and we have an expression for v, it could have more than one solution. In fact, if you have a look here, it's got a value that its derivative is 0 there, and its derivative is 0 up at t0. So if you have an expression for this, then you might get two places. But you reject this because this gives you a minimum. So you have to check, did you get a minimum or maximum? So one of the ways of knowing this is that if this function only has one derivative, in other words, if it just starts out positive like that, then you haven't got a problem, and you'll only get one solution. But you always have to check. So when I say optimize, it may be a maximum or a minimum, but we've got to check that we get a maximum. So we want to find the t that does this, so we want to look at v primed alpha infinity t is equal to, now we've got to take that derivative. So do we know how to differentiate that function? So I'm going to just write down the solution, and you can check that as well when you do your homework. So if we differentiate this, and the steps are in here, what you get is delta p times t plus delta t times t over 1 e to the delta t minus 1. So when you take this derivative and you work through, there's like 3 or 4 steps, you'll finally come to the solution. Now if you look, what we have to do is we have to find where this solution is equal to 0. Actually, this is one. We're going to look at this equation, dv dt at t equal to 0. If we take that derivative, then what we come up with is this equation. So you've got to go through and differentiate this, set it to 0, and then you'll come up with this equation. Okay? So you can just work through that at home. And now we can interpret the principle of if we solve this equation, the solution is going to be what I call p t subscript delta. So when I take this and I solve it, I'm going to get my solution. And so I give it a special name. And that solution I call t subscript delta to indicate that its value depends on the number delta that I've chosen. So this equation will give you different solutions for different values of delta. So if the If the discount rate is 1%, then this will be 0.01. If it's 2%, it will be 0.02. And for different values of delta, so you'll get different solutions. And when delta is equal to 0, you'll get this solution. And as delta increases, so you'll harvest earlier and earlier, depending on the discount rate. Okay. So now can we interpret this? So this is the rate of change of P, which is the value that we accumulate as we wait to perform the harvest. And this is just the solution that we got if we didn't worry about the future. However, this quantity over here, we called V infinity at T delta. So what this is it's the present value of the stand immediately after we've harvested. So this is the site value. And this is the harvest value. So in other words, when we harvest the stand, there's something that we get immediately from selling the trees on the stand. But we still have a stand that we can grow trees on and get profit from in the future. So that's the present value of the stand without the trees, and this is the value of the trees on the stand. So you can put this another way. Value of trees on stand once harvested. And then this is the site value, or the value of the stand, immediately after harvesting. So does everybody understand what happens, how this relates to the original solution? The original, when we started off just with a one-time optimization, is we didn't get this term in here because we weren't valuing the stand beyond that. But once we set up a present value that takes into account repeated harvests for all time into the future, then our equation gets this extra term. And so we have the discount rate delta, we have the value of the trees that we get when we harvest, plus the value of the stand without the trees once we start the process again. So this is called the Faustmann principle. And Faustmann was a forester in Germany, and he came up with this principle in the 1850s. So if you have a look at the material here, so I've got some notes. Unfortunately, in the notes, you'll see that over here, if you open this up, or let me see, yeah, it's missing this term over here. It's kind of obvious once you work through the math. And over here, you're also missing the factor delta. So it's missing that factor. So these are typos that I'm sorry I didn't pick up earlier, but I already had this all prepared. Then there's some, you can go to the textbook, and we don't do this whole problem in the textbook, but we do pieces of it, and we talk about harvesting, and you can get some more background there on optimal rotation period. And you'll see that if V of t has a specific form over here, and the discount rate is 0.1, then you can actually do a calculation. Now, in some books, instead of P of t, they call it S of t, S for stumpage. So I've set up this problem in terms of S, not in terms of P. That's just so that you've got to work through this whole thing again yourself. And why do you have to do this? Because in the midterm, I'm going to ask you the following question. I'm going to say, consider the Faustmann formula for the optimal rotation period t associated with clear-cutting a forest stand, which can be written in this way. So that's this equation over here with S instead of P. And then I say, derive this formula by considering the net present value of the harvest in each rotation period. Provide a verbal interpretation for the terms in there. And then if S of t has a particular form, then I will ask you to derive the optimal rotation period when the discount rate is delta equal to 0. Now, when delta equals 0, over here, if you look at this and you take the equation here, and you look at this particular expression, I'll just make it bigger. If you take this equation and you work it out, and you look at p at time t0, and that's the limit as delta tends to 0 of this expression, then you'll just get p t0 over t0. So in other words, that maximizes the solution when the discount rate is 0. You just have to calculate an equation for which p of t over t. So if you've got a function p of t, you divide it by t, and you have to that sets up your equation for calculating t0. And so you can follow that example in the textbook. Okay? So that's basically the reason why I give you this as a question in the midterm and tell you exactly what it is because the best way for you to learn this stuff is actually to answer that question and prepare it. And then make sure. So you can't bring in the solution. It's got to be in your head. But if it's in your head, it means you understand it. There's just several steps to go through. You set up the problem, you want to maximize it, you take the derivative. You will have seen it in preparing for it. You'll work it all out. You'll see how it works, and you'll know how to present it. And so make sure you prepare it. So now you've got two questions for your midterm. One is going to be a genetic model, very similar to your current homework assignment. Then you're going to have this question. Then there'll be some other stuff on genetics and maybe another question. And that'll be your midterm. Okay, any questions about the material? Anybody object if we finish 20 minutes early? Okay, great, thanks.